All right. Video for physics Hers. The lab. All right. So I was a little bit late in setting that up for you, showing you that. Actually, let me quick pause this, and I'll run and grab the setup so you can see what it is. All right. We took a spring scale and we hung masses off of it. Right. We started off with this empty and added 20 grams at a time and stretch the spring scale. Now the scale itself is fairly hard to read. The little increments go up by 0.05. Um, so it was a little bit tricky, but the results come out pretty well. You know, these spring scales have been abused over the years, so they're a little bit stretched out, some of them. But in general, the results came out well. So the materials are the ring stand, or stand, whatever you want to call it, masses, spring scale. All right. So the whole point here is to determine how the amount of mass, affects the weight of the object. So weight is measured in newtons, which is a capital N, and mass is measured in kilograms, kg, just like from chemistry. There's 1,000 grams in kilograms that will come into play in this lab. So I'll show you the raw data set here. So in here, raw data, I took a picture of a student today in class. This is a very good data set. I will put this kind of over to the side perhaps, and then I'll open up Logger Pro. Make that a little bit smaller so I can see the data. Now, all right. So yeah, it's annoying how Logger Pro does this. When you shrink the window, it makes these super small, but that's okay. So the x-axis, we made mass. All right, so the name there is mass. Oops, caps lock on. Mass, short name, is a lowercase m. And the units for mass is kilograms. Now that's the thing we control that's going on the x-axis. This lab's nice because we can plot the data as it was collected. So mass, short name is lowercase m, units kg. All right. Y was weight. Now, initially we just call this weight and capital W. Now, this is really what this is it's the force of the Earth pulling down on the mass. Force of the Earth pulling down the mass, which is also known as the force of gravity, which is also known as weight. Weight, turns out, is a measure of the magnitude of the force of gravity. So the word magnitude means the size of the force, the quantity of the force of gravity. So the units for weight are newtons. Weight, capital W, force, units, newtons. All right, then we're going to put in the values. All right, 0.13. Now, the little masses are labeled in grams. So the big one and the hook are 50 grams, and each one of these is about 20 grams. So you can see this. So that's why they're all odd numbers for the most part. This group must have used one of the 10-gram masses in there to get the 4 and the 8 on the masses, 80 grams. They must have done a 20 and a 10 on top of the 50. But that's fine. I told them they could do that. All right. So 0.13. You don't need to put these in any particular order. They kind of jumped around, it looks like here. I'm not sure why, but that's totally fine. This data set came out really nice. All right. The weights now. Now all of these, oops. If you hit the down arrow, it should bring you right down. Oh, I hit return is what I did. All of these should be either end in a 0 or like this was actually 1.10. This one was actually 0.70. This one was 1.30. This one here is 1.90. This one is 2.20. This one is 0.65. So they either need to end in a 0 or a 5 because it went up by 0.05 increments. So they only had one that was on the 05. So now, as usual, okay, I'm going to maximize Logger Pro now. All right, so I can see everything here. Usual, this is all jammed in this corner, so we right-click, auto scale from 0, and then we put a fit line in there, R equals. All right. The slope of this line is very good, actually. It came out excellent. 9.8 newtons per kilogram. Now, let me get a little piece of scrap paper here. I'm going to write something on here and hold it up to the, let's see. And of course, I can't find a good marker. Oh, there it is. So the equation of this line says W equals MOM plus P. W is the short name for weight. M0 is the slope. The reason it does M0 for the slope is because we used lowercase m as the short name for mass. So it won't label the slope the same way if you use lowercase m for one of your variables. So one of your short names. So M0 just means slope plus m plus b. So the equation of this line, now I didn't notice this in class when I didn't notice this when I got the data set, but they have a pretty significant y-intercept. All right, and perhaps that means that this group didn't scale their force sensor, right? Because it should have been centered on 0. So all their measurements are shifted down. They're all measuring lower than what they should have. All of them, though, because the slope is great. Correlation's great. The actual numeric value of the slope is great. It's just the y-intercept's a little off. So probably what happened was the plunger on this was probably high above 0 when they started measuring. That made every subsequent measurement an undercount by that amount that was shifted initially. All right, so that's probably what happened there. The y-intercept here should be 0, right? If we have no mass, we should have no force. So since it's showing, or no weight, since it's showing weight at no mass, that means the scale was probably shifted. Probably didn't 0 it, but that's fine. That's a normal thing to do. So I'm going to write the equation of the line here. Capital W equals 9.83 newtons per kilogram times the mass. So there's the experimental equation for this lab. All right, W is the y variable, slope of the line is 9.83, and the x variable is m. All right, that's one of the questions. Now, what is the slope of the line telling us? We talked about this in class today. The slope of the line is telling us the amount of weight each kilogram of mass. Whenever you see per kilogram, you can think of it as being 9.8 newtons. Let me write this on a piece of paper as well. You can think of that as being, I should have a little whiteboard here to hold up for you. You can think about that as being 9.83 newtons per 1 kilogram. You can think of it like that. 9.83 newtons per 1 kilogram. All right. So, you know, you can think of it like that. So that means what it's telling us is 1 kilogram of mass has a weight of 9.83 newtons on Earth's surface. Well, the next question asks, do you think this could be different? And the fact is, yes, this number could be different, but not in our classroom. In our classroom, they should all have the same amount of, every newton of weight should have this, every kilogram of mass should have the same weight in a single classroom. Now, if you travel to the moon, where gravity acts differently, the weight would be different. All right, so mass is mass. That's a constant. You know the mass of something? 1 kilogram of matter is 1 kilogram of matter anywhere in the universe. All right, but the amount of weight that is equal to depends on the gravitational field strength. So that's what the slope of this line is. The slope of this line is the gravitational field strength at Earth's surface. And we give it a name. We give it a variable. You've probably seen it before. Lowercase g. Lowercase g is Earth's gravitational field strength of Earth's gravitational field strength at its surface, or gravitational field strength at Earth's surface. That's the best way to say it. So gravitational field strength at Earth's surface is G. And the theoretical value of G is 9.81 newtons per kilogram. And that's on the physics reference table. It's on your equation sheet as well that I've given you, which I don't know if I've ever posted online for you or not. G theoretical is 9.81 newtons per kilogram. So the strength of Earth's gravitational field at its surface is 9.81 newtons for every kilogram of mass. All right. I think that's about it for the lab. Just make sure you, when you draw your force diagrams, that they're full object agent notation. Don't shorten the names yet. Oh, W? Oh no, that's not really it. So let's go back to this one. Weight equals G times M. Well, it turns out, remember, weight is the force of the Earth. Weight is the force of the Earth on the object, on the hanging mass. Weight equals G times M is like what your finished general equation for this lab would be. There's no write-up for this lab, by the way. It's just fill in the blanks. However, the way we usually write this is like this. All right? We usually write it like that. Fg equals mg. All right? Fg equals mg, where Fg is the force of gravity on an object, the force of the Earth on an object. See, after this lab, we're going to start moving away from object-agent notation, and we're going to call it force of gravity, Fg. But you always need to remember, moving forward, that that force of gravity that is happening here, right? That force of gravity is the force of the Earth pulling on the object. All right, that is so key. Force of gravity is the force of the Earth pulling on an object. And for every action, there's an equal and opposite reaction. So for every time the force of the Earth pulls on an object, the object also pulls on the Earth. So force of gravity on you, well, you apply exactly the same amount of force of gravity on the Earth as well. You're pulling towards each other, just like two ropes pulling against each other. They both experience the same pull. However, my mass is so insignificant compared to the Earth that it has, for the amount in comparison that my mass is insignificant to the Earth, the effect of the force is more significant on me. So the greater the difference in mass between the objects, the greater the effect is on the lighter object, and the lesser the effect on the heavier object, all right? And usually when you say light and heavy, something's light or something's heavy, it's a measure of the weight of it, how much it pulls. It's not the mass necessarily, right? So that's it. Have fun filling out the rest of this lab. You're going to fill it in, full motors, you'll scan it, print it, scan it, or do it on scrap paper, scan it, submit it. All right, that'll be due, well, next time, so B-Day, I guess. All right, I'll talk to you guys later.